Hello, everyone, and welcome back to another Math 104 lecture. So if you're following along in the textbook, the section that we're going to be looking at today is section 3.3. And what this focuses on is polynomial division. So up until this point, the only type of division that we've been doing with polynomials has been factoring. We've done factoring. We've also had rational expressions, which have been in the form of some polynomial over another polynomial. So, for example, x squared minus 1 over x plus 1. This is a rational expression, polynomial divided by a polynomial, right? But we actually haven't division. Up until this point, what we've had is we've kind of lucked out, right? The polynomials up top have generally been able to be factored and then canceled out with the polynomial on the bottom. So there's several methods that we use to divide polynomials, and factoring just happens to be one of those methods. So in the sense that we've lucked out, well, we've already learned one of those methods so far, and then what we're going to be looking at is polynomial long division and then polynomial synthetic division. Now, I have a feeling that because I want to take this a little slow, I really want to make sure that the process is understood well for both of them. I have a feeling that this lecture, this chapter is going to be split between two lectures. So we'll see how much we cover today. I will always adjust the homework as necessary, and we'll go from there. So, polynomial division. You handle polynomial division very, very similarly, as you would handle just division of regular numbers, right? So let's say, we just start with some really basic concepts that we already know. 2 times 3 is equal to 6. And we all know that this is true, right? We can say 2 and 3 are factors of 6. And we know that they're factors because they are in factored form, right? It's just two numbers being multiplied against each other, two whole numbers being multiplied against each other to give you one larger composite number, right? Okay, so when you think about it in this way, again, if you have something like this, you understand that both x plus 1 and x minus 1 are factors of x squared minus 1. You have two numbers, two terms, right? They're polynomials that are being multiplied together. They're in factored form. They're the only thing that's happening between the underlined in red and the underlined in blue is multiplication. They're being multiplied against each other. So you know that they're in factored form. And, as a result, it gives you one larger composite polynomial. So we get x squared minus 1 as a result. And this should look familiar, especially because it's difference of squares, right? Difference of squares. But in any event, the whole point that I'm getting at is that you have two numbers multiplied together to give you a larger number, right? Okay, well, if we take... So let's look at our numbers here. The 2 times 3 is equal to 6. We can rearrange this, right? We know that in an equation, if we do one operation on one side, we could do that same operation on the other, and the equation will stay true. It'll stay, exactly 100%. Nothing has changed other than its appearance, right? So I can take my 2 times 3 is equal to 6, and I can divide both sides by, let's say, 3, for example, and say, okay, 2 is equal to 6 divided by 3. And now what does this tell us? This tells us that we had some larger number, 6, and we're dividing it by another smaller number, 3, and we got 2 out as a result of it, right? We have an operation going on, 6 divided by 3 gives us 2. Now notice that this is another way to tell you that you have a factor, that 3 is a factor of 6. How do you know that 3 is a factor of 6 here? Well, you know 3 is a factor of 6 because when you divide 6 by 3, you get a whole number back. You get an integer of 2 returned to you. So that tells you that 3 has to be a factor because you get a whole number back. So in the same vein that if you divide 8 by 4, you get 2 back, or 8 by 2, you get 4 back. Same ideas, right? Okay, so if we're looking at our polynomials, we can actually do the same exact thing. If we have x squared minus 1 divided by either one of our terms here, we'll just divide it by the x plus 1 instead. So we can say this is the same thing as x minus 1 is equal to x squared minus 1 over x plus 1. And once again, what does this tell you? This tells you that if you're starting with some larger polynomial and you divide it by a polynomial of a lesser degree and you get a polynomial back with no remainder, and we'll talk about what a remainder means in terms of polynomials in a little bit, definitely in this lecture. But the point is that you're getting x minus 1, right? That's definitely a number. That's definitely a whole number. We don't know necessarily what x is, but we know that x is going to be some sort of integer, and when you subtract 1 from it, it's just going to be another integer back. So point is that we're dividing a larger polynomial by a smaller polynomial, and we get a polynomial back. So you know x plus 1 has to be a factor of x squared minus 1. So there's a theorem here, and our theorem, which I've already written out here, and it's a little wordy, but just go with me on it for, just for right now. So polynomial b, or b of x, is a factor of polynomial f of x if there is some other polynomial a of x such that a times b will give you f. Again, a little bit wordy, but let's break it down what it actually means. It means that you know for a fact that your polynomial b is going to be a factor of your larger polynomial f if, when you multiply b times some other polynomial that, a, some other polynomial has to exist such that when you multiply them together, you get f. And when we think about it, if we're trying to consider whether or not x plus 1 is a factor of x squared minus 1, well, think about this like your b of x, and x squared minus 1 is your, f of x. So the theorem says x plus 1 will definitely be a factor of f of x, or of x squared minus 1, if there's some other polynomial that would multiply together will give you that x squared minus 1. And in fact, well, we do have some other polynomial. Some other polynomial is, in this case, x minus 1, right? When you take x plus 1 and you multiply it with x minus 1, you get x squared minus 1. So that tells you that x plus 1 is a factor of x squared minus 1 because there is some other polynomial that exists such that when you multiply them together, you get x squared minus 1 as a result. And then the same can be said about x minus 1 if you started with a of x instead, right? If you started with this piece, and you're asking yourself, okay, is this a factor of x squared minus 1? Well, you're just asking, is there some other polynomial that when I multiply by a of x, I will get x squared minus 1? And yeah, then we know that this is the case. When we multiply by x plus 1, we get x squared minus 1. So it seems fairly intuitive, right? I mean, it was a bit wordy, of course, the theorem, but it's fairly intuitive, especially given everything that we've done with factoring. What I want you to do is keep this theorem in the back of your head as we proceed into long division. But for right now, we're just going to look at our first method a little bit more in detail, which again is factoring. So let me go ahead and clear this. So again, as I mentioned, our first method for polynomial division is factoring. Whenever possible, that's generally going to be the easiest way to do things. So try with the upcoming examples that I'm going to put here. Try following along, and our entire goal here is we're just going to be factoring as much as possible and canceling if at all possible. Okay, so let's start with x squared plus 4x minus 12. And this is going to be divided by x plus 6. Okay, so we have a polynomial of a higher degree on top, right? Our higher degree, it's an x squared, whereas we only have x to the first on bottom. So we know that we definitely can divide this and we can get some kind of result at the end, right? If your polynomials are flipped as far as the higher degree being on the bottom and the lower degree being on top, then you wouldn't be able to get any kind of outcome. It would already just be in the most reduced form of fraction that you could get it. Of course, you could try factoring, but that's not going to get it out of its fraction. And I'll show you an example of that in a second, specifically with the polynomials that we have right now. But for right now, let's just focus on factoring and seeing what happens here. So let's try to factor the top. So x squared plus 4x minus 12. Well, factoring the top, this isn't so bad. We know how to do this. That means we're going to look at factors of negative 12 such that they multiply to give you a negative 12, but add to give you a positive 4. So the ones that come to mind are going to be positive 6 and negative 2. So that means I'm going to have x plus 6 up top, x minus 2, and then I have an x plus 6 over here. And since we're now factored, since I have something times something up top divided by something else, well, we can just cancel the terms that are similar, right? So x plus 6, those go away, and we are just left with x minus 2. So what this tells you is when you take x squared plus 4x minus 12 and you divide it by x plus 6, you get x minus 2 as a result. And going back to the theorem that we just talked about, this tells you by division that, well, by our theorem of division, that if you're wondering if x plus 6 is a factor of x squared plus 4x minus 12, well, you're looking for some other polynomial that when multiplied, against x plus 6 would give you the x squared plus 4x minus 12. And so cleaning this up, well, let's get rid of that middle inside. We have x squared plus 4x minus 12 over x plus 6 is equal to x minus 2, right? This was our result. Our result was x minus 2 as our answer. Now, what I'm about to do has nothing to do with solving the division. What I want to do is just get it into the form that the theorem was talking about. So what I want to do is I'm going to multiply both sides by x plus 6. So multiplying both sides by x plus 6, we get x squared plus 4x minus 12 is equal to x minus 2 times x plus 6. And the reason that I did this is because, again, I wanted it in the form that the theorem was talking about, right? Where we had some sort of b of x, where we had some sort of a of x, and where we had an f of x, right? So again, what this is telling you is if you're wondering if x plus 6 is a factor to the larger polynomial, well, that is essentially asking you, is there another polynomial, a of x, that when you multiply a and b together, you get f? And by division, we have shown that, yeah, it exists. There is an x minus 2 that, when you multiply x minus 2 times x plus 6, you get that x squared plus 4x minus 12. So our answer is x minus 2 when we do that division. Okay, so let's, what I wanted to do is I wanted to give you guys just a quick example of what I mean by if your highest powers are flipped. So let's say we have the same polynomials, but just in on the flip side of the fraction, right? So x plus 6 in the numerator now, and x squared plus 4x minus 12 in the denominator. Okay, so what I mean by this is always going to be a fraction. You can try to simplify the fraction, but you're never going to be able to get it out of a fraction because, again, notice your highest power here is a 1 up top, and your highest power on bottom is a 2. So if you have the case where your highest power of the whole fraction is in the denominator, then you can try to reduce it, but it's always going to be a fraction. So you follow your same steps, right? And in our same steps, we found, x plus 6 on top. We know that this factors to be x plus 6 and x minus 2, as we just did above. Cancel things, cancel out the x plus 6 and the x plus 6. Notice that we're left with a 1 over x minus 2. So this is still a fraction. We haven't been able to get it out of a fraction, but there is one important piece here that you should note. We started with x to the first, and it was being divided by, if we're talking about just leading terms here, our leading terms are x on top over x squared. So what happens if you have just x divided by x squared? Well, that's the same thing as x divided by x times x, right? X squared is x times x. We know that one of them are going to cancel, right? X divided by x, that's going to cancel out, and you're just left with 1 over x remaining, right? So this is going to be of the order of 1 over x, minus whatever, or x plus whatever. So there's, going to be some jargon here because we were only talking about our leading terms here. But again, this should make sense that you end up with a 1 over x minus 2, because when we're talking about our leading terms, it was x to the first over x squared, and you know that one of those x's is going to cancel out, leaving you with a 1 over x situation. So again, this should make sense that your highest power in the denominator is now an x to the first. Okay, so with all that being said, let's look at a little more complex examples of factoring. So would love to erase everything. There we go. Okay, so let's say we have x cubed minus 1 divided by x minus 1. Okay, so we haven't really looked too much at factoring cubes, but we did talk about it a little bit in the beginning, and specifically difference of cubes is something that we talked about. And I brought up the device that you could use to help you remember, SOAP, right? SOAP means same, opposite, always positive. And what we're talking about here is the signs of the outcome of, when you factor this. So if we're talking about difference of cubes, it's in the form of a cubed minus b cubed. And when we factor this, this gives us, well, again, so same sign, opposite sign, and always positive, SOAP, right? So that means we're going to have a minus b, so same sign. Then we're going to have a squared. Then we have the opposite sign, so now it's going to be plus. And this is the only part where things kind of get a little bit tricky. It's just instead of a squared plus or minus 2ab, like we used to see with quadratics, it's just ab. So there's no 2ab, it's just ab here. So we have s O, so same sign, opposite sign, and then always positive, right? So this piece is always going to be positive, and we get a b squared at the end. So this is going way, way back, several lectures, almost like to the beginning of when we first started, but this is difference of cubes, right? So what we know here is, okay, well, we have an x cubed. And we know that 1 is the same thing as 1 cubed, right? 1 cubed is still just 1, so we just change the form of it so that way we can match our factoring scheme here. And now we just factor according to our blueprint, right? So factoring here, that's going to give us, well, we're going to have an x minus 1. Then we're going to have an x squared. Now we flip the sign, right? We had the same sign. Now it's opposite sign. So in this case, we're going to have opposite sign, so plus. Then we have a times b, so x times 1, which is just x. And then, last but not least, we have b squared, which is 1 squared, which is just 1, right? So just 1. And this is all over x minus 1. And now we see, oh, yeah, we have an x minus 1 up top and x minus 1 on bottom. So when we cancel these, we are just left with x squared plus x plus 1. Again, our process is the same for factoring, right? Even though it was cubes, our process was the same. We just had to know how to factor a cube. But now that we know how to factor difference of cubes, or that we should have known how to factor difference of cubes, even if we haven't gotten much practice with it, then we realize we have the same factor on top and bottom, and we cancel that factor, right? It crosses out, and whatever we're left with is what we're left with. So in this case, x squared plus x plus 1 is going to be our answer for x cubed minus 1 divided by x minus 1. Okay, so let's do one more together, and then I'll set you off on your classwork. So we just talked about cubes, right? So factoring cubes. Let's do one more with cubes. Let's say we have x cubed plus 7 over x plus 2. Okay, so before we proceed, we have to ask ourselves, okay, well, factoring difference of cubes and factoring sum of cubes are exactly the same thing. So if we're talking about sum of cubes, a cubed plus b cubed instead, you're still going to use SOAP. So you're still going to have a plus b, so same sign, right? So a plus b, so s. Then we're going to have a squared. Now we're going to have o, so opposite, so we have minus. Then it's a times b, and last but not least, always positive, right? So now this is a plus, and we get b squared at the end. Okay, so factoring difference of cubes, we know how to do it, but do we have, or I'm sorry, sum of cubes, we know how to do it, but do we have a sum of cubes? Well, we have x cubed, and then we just have to ask ourselves, is 7 a cube? Well, technically, I suppose, right, 7 is the same thing as this, right, the cube root of 7 cubed, right? So 7 is still technically a cube, but we can do a little bit better here, because if we try getting it in this form, if we replace 7 with, the cube root of 7 cubed, then it's not really going to help us with our division of x plus 2. So we need to kind of look ahead. We need to ask ourselves, okay, what is this x plus 2 going to factor with, right? So we say to ourselves, okay, well, what if instead of a 7, this were an 8, right? So instead of, just hypothetically, instead of it being a 7, let's pretend that this was x cubed plus 8. Well, if we factored x cubed plus 8 according to our blueprint above, well, factoring x cubed plus 8 is going to result in 8 is the same thing as 2 cubed, right? So I could replace my 8 with a 2 cubed, and then, oh, yeah, we're going to have an x plus 2 here, and that's going to that's going to cancel with our denominator of x plus 2. So our dream here is to be able to get an x plus 8, but we're starting with, an x cubed plus 7. If we can get this, this to be an 8, then we'll be golden. So what I'm going to do is I'm going to do the trick that, I've been trying to tell you guys before, and that's, adding 0. We use this trick when we're completing the square, right? So the idea is we add something that we want, but with adding, we always have to take something away. So to keep the equation balanced, to keep the fraction balanced. So I'm adding 1 and subtracting 1 with the idea that, okay, if I just simplify this piece, that's the same thing as adding 0, right? I'm not changing my total, the total value of the fraction. But what I am going to do is I'm going to add the 7 and the 1 together, so that way I do get an 8. So now I have x cubed plus 8, and now I just have this minus 1 lingering around. And I'm going to put parentheses around this because this is the piece that I want to factor. So I have x cubed plus 8 minus 1 all over x plus 2. For the interest of space, I'm just going to come down here. So what I'm going to do now is I'm going to factor this piece in the parentheses, and then we'll just have that minus 1 lingering around in, which we'll deal with later on. So x cubed plus 8. Again, we already established 8 is a cube, right? 8 is the same thing as 2 cubed. So this is really the same thing as x cubed plus 2 cubed minus 1 outside over x plus 2. And when we factor this, now we can factor and do the same opposite, always positive, right? We can use SOAP to help us figure out the sum of cubes when we factor. So this is going to be x plus 2, right? A plus b is our first term when we're talking about this. A plus b right here. So that's going to be our first piece, x plus 2. And we know it's a plus because s, right? S part of SOAP, same sign. So x plus 2. Then we have x squared. Now the next thing is going to be O, right? So opposite. So we have a minus. Then we have 2 times x. A times b is the middle piece. And last but not least, we have always positive. So plus, and then b squared, which is 2 squared, which is 4. And we have that minus 1 lingering around on the outside, even though we factored the sum of cubes. We have this x plus 2 on the bottom. Okay, well, we're doing really good. We have this x plus 2 on top. We have this x plus 2 on bottom. We can almost cancel it. The problem is that you can only cancel things in a fraction, regardless if it's polynomial or if it's actual numbers, whatever the case may be. You can only cancel it if your top and bottom are already factored. Are we factored entirely on the top and bottom? Well, the answer is no, right? We have multiplication going on, x plus 2 and the x squared minus 2x plus 4. Well, that piece is factored, but we have this minus 1 lingering around. So what I'm going to do is I'm going to split this into 2 different fractions. My idea here is I'm going to keep the pieces that are factored together, and then I'm going to have this minus 1 all by itself in a different fraction. And now, this might seem weird, but remember common denominators and how we handle fraction addition and subtraction, right? Normally we're used to seeing it going, combining into one fraction. Well, now what I'm going to do is I'm going to split it up by, the same common denominator. So just as a reference of what I'm talking about, if we had, for example, 1/2 plus 3/2, well, you needed common denominators, which you have here, 2 and 2 on the bottom. And then what could you do? You can take your 2 fractions and make it 1 fraction with the same denominator, right? So you can make it 2, and then you would just add your numerators or subtract your numerators if that were a subtraction sign instead. So what I'm doing is I'm going in the opposite order. I'm starting with one fraction, and because I have something minus something else, I'm going to split it into two different fractions. So I'm going to have x plus 2 times x squared minus 2x plus 4 over x plus 2 minus 1 over, and now we keep the denominator the same, so 1 over x plus 2. Again, all I did was I separated them into two different fractions, right? Everything that was factored, I kept together, and everything that wasn't factored, so, the minus 1 piece over here, I threw in the other fraction, so minus 1 over x plus 2. And we just keep the denominators the same. It's the same thing, again, as if we had, just regular numbers, right? 1 plus 3 over 2 is the same thing as 1 over 2 plus 3 over 2. And we just, separated the fractions. So now what can we do? Well, now for this fraction, we see that, oh yeah, things are entirely factored. We can do our cancellations now. So the x plus 2 over the x plus 2 as desired, right? That was the whole idea behind changing the 7 to an 8. So that way we got this x plus 2 piece. So now that that canceled out, we're left with x squared minus 2x plus 4 is minus 1 over x plus 2. And you ask yourself, is there anything else that we can do with this? And the answer is no, right? Just like we saw earlier when we were talking about the degrees of, if you had a higher degree in the denominator than you do in the numerator, the best that you could do is you can simplify it, right? You could simplify the fraction, but you're always going to have a fraction. You're always going to have a remainder. You're always going to have something left over. And in this case, your power in the bottom is x to the first, and your power up top, even if it doesn't seem immediately available to you, is x to the 0, right? We know that any number to the 0 power is just 1. So your power in the numerator is x to the, or is a 0. So we do in fact have a higher power on bottom than we do on top. So we know that this is the best that we can do. We can simplify this to just 1 over x minus 2, and that's the best that we can get. So if we're asking ourselves what this division leads to, if we're talking about just this piece here, x cubed plus 7 over x plus 2, the answer to this is you get x squared minus 2x plus 4 with a remainder of 1 over x minus 2, a negative remainder of 1 over x minus 2. Okay, so the idea is the same, right? If we're talking about, let's say, 37 divided by 7, you know that 7 is not going to go evenly into 37, right? So 7 goes, 7, 14, 21, 28, 35. So we know that you're going to get 5 because 30, when you plug 7 in, you know that the biggest number that you could take out is 35. So you know that you're going to get 5 and some remainder, so something left over, right? So 2 over 7. So the idea is going to be the same with polynomials, and we see that in this case right here, where it's not going to go cleanly into it, right? You're going to always have something left over. So that is the case. Okay, so what I want you guys to do is go ahead and try your first classwork assignment. So the first classwork assignment is, somewhat of a difficult factoring problem. So I want you to factor and cancel, if at all possible, to help you solve the division. So the classwork is x to the 4th minus 1 over x plus 1 times x minus 1. Okay, so give this a shot, see what you can come up with, and we'll take it from there. Okay, so what we're going to do here is we're going to factor, right? So luckily for us on the denominator, that's already factored. We don't have to do any sort of factoring for the denominator. But for the numerator, we do, right? So we have to examine this x to the 4th minus 1 piece. Well, what do we know about exponents? Let's talk a little bit about one of our exponent rules. If we have something like this, where we have a base raised to 2 numbers being multiplied together, we always know we can separate those exponents, right? We can make this, a to the n to the m, or we could also put, we can flip the order of the exponents. So we can make it a to the m to the n. And it doesn't matter. These are all equal, right? This is one of our exponent rules. So we ask ourselves, okay, well, what is 4? 4 is a composition of a couple numbers, right? We can definitely break 4 down here. And the reason I want to break 4 down here is because I know that 1 is the same thing as 1 squared. And I know that I have this subtraction sign. So if I can somehow manipulate x to the 4th to look like a square, then I have difference of squares, and then I can factor this. So x to the 4th, using my exponent rule here, well, this is really the same thing as x squared squared, right? When you have a base raised to an exponent raised to another exponent, you multiply those exponents together. So going backwards, if we were to go this way, just to check our work, you would multiply 2 times 2, and yeah, you would get 4. So x squared squared is the same thing as x to the 4th power. So what does this tell you? Well, this tells you that you do, in fact, have a square. You have that minus 1, and 1 is the same thing as 1 squared over x plus 1 and x minus 1, right? So the idea here is, yeah, we can absolutely factor the numerator by difference of squares. So difference of squares tells us we're going to have a plus b times a minus b. My a in this case is x squared. Instead of it normally being, we're used to it being x, our a is x squared because that's the entire piece that is also being squared. So we're going to have x squared plus 1, so a plus b, and then x squared minus 1. And this is all over x plus 1 and x minus 1. Okay, we're still not done yet, right? Is there anything that we can immediately cancel out? And the answer is no, but we know that we can factor something again here. Now, you ask yourselves, can we factor x squared plus 1? And the answer is no, right? We have a square. We know 1 is the same thing as 1 squared, but we don't have a difference. And in fact, when if you were to try to get an answer for what x is by plugging this into the quadratic formula, we've already talked about how you're not going to get a real number, right? You're only going to get complex solutions. You cannot factor x squared plus 1. But x squared minus 1, we can absolutely factor again, and we see, oh yeah, squared, squared, difference. We can do another difference of squares. So we keep the x squared plus 1 hanging around. Then we have times x plus 1 and x minus 1, right? Difference of squares, a plus b times a minus b. And when everything is said and done, we see we have the same factors on top that we do on bottom. So our x plus 1 cancels with the x plus 1, x minus 1 cancels with the x minus 1, and the only thing that we have left is x squared plus 1. So when you have x to the 4th minus 1, and you're dividing it by x plus 1 times x minus 1, your final answer is just going to be x squared plus 1 with no remainder, right? The key here is notice there's no fraction, there's nothing left over. So what this tells you is that x squared plus 1 has to be a factor of x to the 4th minus 1. Because there is no remainder, you know that this is a factor. And you also know that your divisors are factors. Okay, so that's that for factoring and for, clearing fractions as best as you can. So that is, your first method for handling polynomial division. Now, the next method that we're going to talk about here is long division. So polynomial long division. Now, what I want to do is I want to give you guys a brief refresher of long division with, actual numbers. And then what we're going to do is we're going to compare the steps that we did with the actual numbers to the steps with polynomials. So let's say we have 315 divided by 7, right? Okay, so with long division, what we're going to do is we set this up in the following form. So 7, and then you put 315 inside the box, right? Okay, so the way that you handle this is you take your divisor, in this case 7, and you see how many times it can go into a number, right? So first you ask yourself, okay, can 7 go into 3? Can 7 go into 3, and will I get anything as a result? And you say no, right? 3 is a smaller number than 7. You can't divide 3 by 7. So you move on, and now you make it, instead of 3, you make it 31 now, right? So now you ask yourself, okay, how many times can 7 go into 31? And you say, okay, well, if I multiply 7 times 4, I get 28, right? That's the largest piece that I can take out of 31. So we put a 4 on top, we multiply 4 times 7, and we know that, that's going to give us 28, and then we subtract. So the idea here is you figure out what the largest piece you can take out, then you multiply your, the 4 times the 7, that gives you that largest piece that you can take out, and then you subtract that piece. So 31 divided by 28 gives you 3, and now you ask yourself again, can 7 go into this number? And it shouldn't be able to, right? The reason it shouldn't be able to is because we already took out the largest number that we were supposed to be able to take out, right? The largest number that we could have taken out of 31 was 28. So there's no way that we'd be able to take out 7 from that remainder of 3. But what we do now is we take our number, our 5, we drop it down, and now this becomes 35. Right? And now we play the game again. How many times can 7 go into 35? Well, 7 actually goes cleanly into 35 when we multiply it by 5, right? So we know that we're going to have a 5 here, and we play the game again where you take your number that you figured out, you multiply it by your divisor. So 5 times 7 is 35, and then you subtract. Right? And then 35 minus 35 is 0. There's no remainder. There's nothing left over. So you know that 7 is a factor of 315. And you also know that 45 is a factor of 315. You know this because, well, there's nothing left over. So that's your step for long division. And hopefully you guys have seen this before. I imagine you guys have seen it before, but it's probably been some time and everybody relies on calculators these days. So this is, probably a good refresher for you. Okay, let's say we have the following. Let's say we have x squared plus 6x plus 5 divided by x plus 1. And what I want to do is I want to solve this by long division. Okay, so solving this by long division, what that means is I'm going to take my divisor, put it on the outside of the box, and on the inside of the box I have x squared plus 6x plus 5. So what was our first step here? Your first step for long division with numbers is you're looking to see if your divisor can go into your first number, right? And we established that in this case you couldn't. But let's look over here. Your first thing that you're going to do is you're going to ask yourself, okay, I just want to concern myself with the x. Don't worry about the plus 1 just yet. Let's just concern ourselves with the x. What do I have to multiply x by to give me an x squared? I have to multiply x by something to give me an x squared. And the answer is x, right? If I multiply x times x, that gives me an x squared. So that's fantastic. We know that we want to multiply by x. So we put our x up top. And what we do is the same thing that we did over here, right? Notice that, for each step, we took our 4, multiplied it by 7, and then we subtracted, right? Or we took our 5, multiplied it by 7, and then subtracted. So what we're going to do is we're going to take our x, and we're going to multiply it against the whole thing, x plus 1, not just the leading x, but the whole thing. The leading x just is, your tool to help you figure out what you need to actually, multiply by. But in this case, you're taking your x and multiply it by the entire divisor. So now, multiplying it by the entire divisor, that gives us x squared plus x, right? X times x gives you x squared. X times positive 1 gives you a plus x, right? So it gives you that. And then what you do is the same thing you do when you're doing your long division of numbers. You subtract the entire piece, which means you're flipping the signs of the entire piece, right? So now you have x squared minus x squared, which should give you 0 as intended, right? That was the whole idea. We're trying to take the largest piece that we can out of, the total polynomial, the larger polynomial. So x squared minus x squared gives you 0. So great. These pieces are going to cancel out. You're done with that, the x squareds. Now you have 6x minus a positive x, which is the same thing as 6x minus x, and that gives you 5x. And what do? You bring down your next term, so you bring down this plus 5. Okay, so moving on, you now have to ask yourself, okay, what do I have to multiply x by to give me a, to give me a 5x? So I have to multiply x by something to give me a 5x. Well, this is already x to the first. This is x to the first. So we just need to concern ourselves with the coefficient, right? The coefficient here is a 1, and my coefficient here is a 5. So I just need to multiply by 5. So we put a plus 5 because I'm multiplying by a positive 5 here. And we take our positive 5 and multiply it by the entire divisor. Once again, the entire thing. So that's going to give us 5 times x gives us 5x. 5 times a positive 1 gives us a positive 5. And we know we subtract the entire thing. So 5x minus 5x gives us 0. 5 minus 5 also gives us 0. So we just get a remainder of 0, which is no remainder, which tells us, yeah, x plus 5 is a factor of x squared plus 6x plus 5. And also, x plus 1 is a factor of x squared plus 6x plus 5. We figured out that both of these are factors because our remainder is 0 when we do this division. And if you want to check your work, well, this isn't really so bad to factor, right? If we wanted to do it our first way, our factoring method, x squared plus 6x plus 5 over, what was it, x plus 1 over x plus 1. Well, let's go ahead and factor the top just to check our work, just to make sure that, we did this correctly. So we're looking at, our C term, which is positive 5. So two numbers that multiply to give you a positive 5, that add to give you a 6. Well, that's, of course, positive 5 and positive 1. So x plus 5, x plus 1, and we're dividing by an x plus 1. And so we know these are going to cancel out, and you're just left with x plus 5, which is exactly what we got here, x plus 5. And just do me the favor, guys, when on your quizzes or on your tests going forward, just please do me the favor of actually writing your answer. So sorry, give me 1 second. I just want to erase everything. So once you do your division here, if you could just write your answer at the bottom, x plus 5, and then circle it, I'd really appreciate that. Leaving it up here can get a little bit messy, especially when you're if you've made mistakes and you have to cross things out. So just write your final answer at the bottom after you've done your long division. Okay, so great. We now have a process for doing polynomial division. Let's do another one together here. So let's go ahead and clear this. Let's say we had, let's do a slightly trickier one. Let's say we have 3x to the 4th minus x cubed. I'm sorry. Whoops. I was messing up there. Let's say we have 3x to the 5th plus 5x to the 4th plus x plus 5. So 3x to the 5th plus 5x to the 4th plus x plus 5. This is all being divided by x plus 2. Okay. So the way that we set this up is the same thing, right? You put your x plus 2 outside the box. So x plus 2, we make a box, and we write our terms, again, in descending order, your highest power first, right? Descending order, highest power first. 3x to the 5th comes first, plus 5x to the 4th. And let me expand the box here. And now we ask ourselves, well, wait, we have highest power to the 5th, and we're going down from the 5th, right? And then, so we have to the 5th, we have to the 4th, but notice we don't have anything to the 3rd or squared, right? X to the 3rd doesn't exist, and x squared doesn't exist. What you have to do when you're writing your powers in descending order for long division to work properly of polynomials, you have to have placeholders. And what I mean by placeholders is you have to put a plus 0 x cubed. 0 times x cubed is just 0, right? So we're not adding anything. We're not, including anything that shouldn't be here, but we need to have a placeholder so that way we can drag things down as necessary. So we have plus 0x cubed plus 0x squared plus x plus 5. So whenever you're doing long division, or synthetic division for that matter, which we're going to get to, if not today, then in the next lecture. So whenever you're doing polynomial, long division, or synthetic division, you always have to put placeholders for the powers that aren't there. So again, we notice there is in our original, there is no x cubed, there is no x squared. So you have to put plus 0x cubed and plus 0x squared for this to work out properly. Okay, but now that we have our placeholders, and I'm just going to erase this here for the purpose of space. Now that we have our placeholders, we are going to go ahead and start our process, right? So we take our first leading term here and we ask ourselves, okay, what do I need to multiply x by to give me 3x to the 5th? So I know that my coefficient here is 1 and my coefficient here is a positive 3. So I know for fact that I need to have a 3. right? So I need to multiply by a 3. And then I need to multiply my x by some other amount of x's to give me x to the 5th. So x times x to the 4th would give me x to the 5th. So now we know we're going to take our entire, what we just found, our 3x to the 4th, and multiply that by our entire divisor of x plus 2. So we get 3x to the 5th as designed, right? That was what we were trying to get because we wanted our first term to cancel out, so perfect. And now 3x to the 4th times a positive 2 gives me a plus 6x to the 4th. And remember, we are subtracting the entire thing. So we have 3x to the 5th minus a positive 3x to the 5th, which is just, minus 3x to the 5th. So we know that these are going to cancel out. So that is just going to give us 0. And now we have 5x to the 4th minus 6x to the 4th. So we are left with a negative x to the 4th. Okay, next thing that we do is we pull down our next piece here, right? The 0x cubed. And the reason we pull this down is because we have two terms that we're dividing by. Now, I want to make this clear. If we're dividing by just one term, well, for the record, this gets a bit trivial if you're dividing by just one term, and I can go over that if anybody wants to see that in private, but try it out on your own, see what happens. But the point is, if you're dividing by just one term, you only need to have one term ready. But the reason that we're pulling down this 0x cubed is because remember that whatever we, put up here, we're going to end up multiplying by this entire thing, and that's going to give us a divisor or a subtraction of two terms, right? We multiplied by 3x to the 4th to our divisor of x plus 2, and we got this piece right here. Notice again, it's two different terms. It's 3x to the 5th and a 6x to the 4th. So we're subtracting two terms at a time because our divisor is two terms. So we need to always make sure that we have not one term, but two terms. So we pull down the 0x cubed because we need two terms. So plus 0x cubed. Okay, now we play the same game. What do I need to multiply x by to give me a negative x to the 4th? Well, again, your coefficient here is a positive 1. We need a negative 1. So we know that we're going to need a negative up top, right? We know we're going to need a negative 1. Okay, and now we just ask, okay, to get to x to the 4th, we need to multiply by x cubed, right? So we need to multiply by a negative x cubed, negative 1x cubed. So negative x cubed times x gives me a negative x to the 4th. And then negative x cubed times the positive 2 gives me a minus 2x cubed. Now remember, we are subtracting the whole thing, so that means your signs are going to flip here, right? So instead of it being a negative x to the 4th, when you subtract it, it's a positive x to the 4th, and that is good because we have a negative x to the 4th up here. So right up here. Sorry, I didn't draw the arrow. So now what we have to do is, okay, well, negative x to the 4th minus a negative x to the 4th is the same thing as negative x to the 4th plus x to the 4th. So when we do this piece, we get a 0 here, right? Just like we had intended. So we get a 0, and now we just have to ask yourself 0x cubed minus a negative 2x cubed. Well, that's the same thing as plus 2x cubed. So 0x cubed plus 2x cubed just gives you, well, that should just give you 2x cubed, right? So we get 2x cubed right here. Okay, we bring down our next piece. So we bring down the x squared, so our plus 0x squared, and now we play the game all over again, right? 2x cubed. What do I need to multiply x by to give me a 2x cubed? I'm going to go through this one a little bit faster now because we should understand the game. Our coefficient of x is 1. We need to get to a 2, so we know we need to multiply by positive 2, and to get from x to x cubed, we should have an x squared here. So now we multiply 2x squared by our entire divisor, x plus 2. That should give us the 2x cubed piece. And then 2x squared times a positive 2 is 4x squared. So plus 4x squared. We subtract the entire thing. 2x cubed minus 2x cubed is 0. Perfect. It worked out. And now we do the next piece. 0x squared minus 4x squared gives you negative 4x squared. Okay, we bring down the next piece, which is the x. Sorry, I'm starting to run out of room here. So, okay, so plus x. And so we have negative 4x squared plus x. We need to play the same game. So to get x to negative 4x squared, well, this should make sense. So we multiply by a negative 4x. So, and again, if it's hard to see, just to go over it, our coefficient of x is 1. We need to get it to a negative 4, so we multiply by a negative 4. And then x, to get to x squared, you just multiply by an x, right? So we have minus 4x against our entire divisor of x plus 2. And we know that that's going to give us a minus 4x squared here. And then negative 4x times a positive 2 is the same thing as minus 8x, right? So minus 8x. And we are subtracting the entire piece. So subtracting the entire piece, negative 4x squared plus 4x squared gives us 0. Perfect. And now we have positive x plus 8x, right? The two negatives make it a positive 8x. So now we get 9x. And we're almost done here. We have one less thing to bring down, right? This positive 5. So bringing down the positive 5 here. And for the record, you don't actually need to draw your arrows. I'm just drawing the arrows here to show you guys what I'm bringing down for each step. I understand that it can make this pretty cluttered. So if you don't want to draw these arrows, totally fine. You don't need to. But in any event, so we have this 9x plus 5. So what we need to do is we need to figure out what I need to multiply x by to give me a 9x. And, well, that should just be 9, right? I just need to make it plus 9. So now we have, okay, 9 times x gives me a 9x. And then 9 times that positive 2 from our divisor gives me a positive 18. And remember, we subtract the whole thing. So 9x minus 9x gives me 0. And then 5 minus 18 gives me a negative 13. And we are done, right? There's nothing else that we can pull down. We pulled down the 5. That was the last thing. And we can't simplify by dividing by, any form of x plus 2 anymore, right? Negative 13 is just negative 13. That's, we end up with what we have here. So what we end up with for our final solution is everything that we had up top. 3x to the fourth minus x cubed plus 2x squared minus 4x plus 9, and then the remainder, right? And you might be wondering how we write our remainder. So first, let me write down our answer. So 3x to the fourth minus x cubed plus 2x squared minus 4x plus 9. And then we had this remainder, right? So it's a negative 13 as a remainder. The way you put a remainder is you put whatever the sign it is. So in this case, it's a negative, right? It's a negative 13. So I put a minus. It's 13 over the divisor. So our original divisor is x plus 2, right? So you toss your remainder over the divisor. I know that some of you guys probably have seen something in the form of like writing in R. So like you write R as your remainder, and then you write negative 13 over x plus 2. Don't do this. Don't do this. Starting from this class and going to any other math class going forward, don't actually write a big R for your remainder. Just include it as part of your answer as, a fraction, okay? Because that is as simplified as you can get this. So you ask yourself here, okay, we got our answer. We did our long division here. Is our x plus 2 a factor of 3x to the fifth plus 5x to the fourth plus x plus 5? Is x plus 2 a factor? And the answer is no. X plus 2 is not a factor, and you know it's not a factor because you ended up with a remainder. When you end up with a remainder, you know that you do not have a factor. You know your divisor is not a factor. Okay? Okay, so I've been going on for just about an hour here. Let's see. I want to just finish up long division as best as possible. Let me do one more quick example here. Then I'll set you guys off on your classwork assignment, and then we'll call it for today, okay? So what was the classwork assignment that I just had you guys do? The first classwork assignment. The first classwork assignment I had you do was x to the fourth minus 1 over x plus 1 and x minus 1, right? Keep this in the back of your head. The reason I want you to keep this here is because I want you to, we want to figure out how we handle when we're dividing by something that's not just x, say like x squared, right? So let's do an example here where we have 3x cubed plus 4x squared plus 7. And I want to divide this by x squared plus 1. Okay, so the idea here is, well, you set this up the same way. You have x squared plus 1 outside the box. And then inside the box, you have 3x cubed plus 4x squared plus 7. Okay? You play the same game. Just because this is a square does not change anything. Okay? So what you're going to do is you're going to figure out, okay, well, I have an x squared, and I want to be able to make it a 3x cubed. So I know I need to multiply by 3. And I also know that to get from x squared to x cubed, I need to multiply by an x, right? X squared times x gives me x cubed. So we take our 3x, multiply it by our entire divisor. So our entire divisor is x squared plus 1. So we have a 3x cubed. And then 3x times a positive 1 gives me, well, what should that give me? That should give me a positive 3x, right? So did we make a mistake at any point? Well, not necessarily. Also, the one mistake that I just made is I realized I should have a plus 0x here, plus 7. Right, the entire idea is you always want to put your placeholder. So we didn't have a x, so we made sure that we have a 0x as a placeholder here. Okay, so sure, we have 3x times x squared plus 1. 3x times x squared is 3x cubed, and 3x times the positive 1 is 3x. So now we're going to bring down that 3x. So we have plus 3x. So plus 3x. The trick here is you're going to line it up with the column that it's supposed to go to. So because we have, we're subtracting the x cubed off, that's cool, and we have 3x plus 1, which gives me a 3. Put this in the column that it should go with. So the column that should go with is just the x's. Okay, so now I'm going to have the subtraction here. And when I do the subtraction, I'm going to end up with, okay, so my first piece is going to cancel out, right? 3x cubed minus 3x cubed, that goes away. What's happening to my 4x squared here? Well, nothing, right? I'm not actually getting rid of an x squared. So my 4x squared is this piece is staying exactly the same. So I'm going to actually drop this down. We're going to have 4x squared here. And now I have 0x minus 3x. So that should give me a minus 3x here. Okay, so sometimes you're going to have situations where you're going to skip a term in the middle, as we just see here, and that's just purely as a result of, figuring out what you need to multiply by to cancel out your first term. So we realized we needed to multiply by a 3x to get rid of our first term of 3x cubed, and when we did that, we were subtracting from the x column, not from the x squared column, and that's okay. That can happen. So we just bring down our 4x squared into the next thing that we're going to bring down because 4x squared is our highest power now. So to handle 4x squared, we ask ourselves, okay, what do I need to multiply x squared by to get 4x squared? And that's just a plus 4, right? So 4 times x squared gives me a 4x squared. And then 4 times plus 1 is just plus 4, right? So once again, we see we're skipping this column here, and we have a plus 4 over here. So minus the whole thing, and we see that we're taking from the 7 column. We're taking from that ones column now, right? So 4x squared minus 4x squared, that cancels out, and then 7 minus 4 just gives you a positive 3 remaining. So we have 3, we bring down our negative 3x plus 3, and we ask ourselves, is there anything else that we can do here? Well, minus 3x plus 3, this is our highest power is 1, right? We're dividing by a highest power of 2, so no, there's nothing else that we can do. So our final answer is just 3x plus 4 with a remainder. So we have 3x plus 4 with a remainder of 3x plus 3 over x squared plus 1. And this would be your final answer. Okay, what's the idea here? Again, just to go over this, well, your process is the same for at least starting. To start, you're looking to see, you look at your leading term here. What do I need to multiply by to get my leading term in here? When you figure that out, which in this case was 3x, you multiply that by your entire divisor. Now, the reason that it might seem strange is because notice how we are excluding a factor of x here, right? We're jumping right from x squared to our constant. Normally, you would have x squared plus some x plus 1, but in this case we don't. So as a result, notice how we're skipping the x, we're skipping our middle term each time, right? We skipped the x squared when we were subtracting an x cubed, and we skipped the x column when we were subtracting by x squared. So the reason that it seems strange is because we're missing, the x column in our divisor. If it helps you understand this better, what you could also do is you could, instead of writing it as x squared plus 1, you could do the same trick that we do with the, by putting a placeholder here. You could make it x squared plus 0x plus 1, and that would solve your problems, right? Why would this solve your problems? Well, the reason it would solve your problems is because you have 3x times x squared, which would give you the 3x cubed, then 3x times 0x. Well, 3x times 0x is just going to give you 0, right? So 0x squared. So we would have plus 0x squared in here, which you see, oh yeah, that doesn't change anything, right? 4x squared minus 0x squared is still just going to give you 4x squared. So if it helps you conceptualize this better, if you have trouble making sure that things are going to go in the correct columns, feel free to add this placeholder in here if you put the necessary things in the correct columns when you're doing the subtraction. Okay, so, and then just following up with what I mean here in the next side. So here again, we have 4x squared minus 3x. Well, we realized we needed to multiply by 4. So multiplying by 4 against x squared gives you 4x squared. And now with this placeholder of 0x in your divisor, 4 times 0x is the same thing as, well, plus 0x, right? And what's going on here? Well, minus 3x. So negative 3x minus 0x still leaves you with negative 3x. So we see here that nothing is actually being impacted. And now with this placeholder of 0x here, it becomes apparent that what you're really dividing by is 3 terms, right? 1, 2, 3. And so what's really being impacted? 3 terms at a time, right? We impacted the and I'm just going to put little red dots here. We impacted the cube. We impacted the x squared, even though the x squared didn't change because we have a placeholder of 0x. We were still doing some operation in that column, and we were doing 0x, right? So we did 3 columns at a time because we have x squared, then no x's, and then a 1, for our ones column. And then again, how many columns did we impact at a time? Well, for our next thing, we had our x squared, we had our x's, and then we had our ones column, right? We had 7 minus 4, which gave us a positive 3. So notice that we also did have the 7 here to make this work out. So the entire idea that I'm trying to convey here is you should, whenever possible, to make it easier for yourself to help conceptualize it, is however many terms you're dividing by, that's the number of terms, or that's the number of columns that are going to be impacted at a time. So again, we have x squared plus 0x plus 1. Well, that means that you're going to be impacting 3 columns because you're dividing by 3 terms. Now, when it was just x squared plus 1, it didn't seem that way because there were just the 2 terms. So x squared plus 1, that's what we were originally dividing by. And again, it didn't seem that way, but in reality, that's what was going on. And that's why we were skipping, this middle column each time. Because, realistically, we weren't necessarily changing the middle column, but it did involve the middle column. So what I'm trying to just get at here is that your process is very similar. Just be aware that you're subtracting things from the correct column or adding things to the correct column. Okay, so again, notice that we paired up our 3x here with our x column. And notice again, we paired up our 4 here with our ones column. Okay. So with that being said, let's just jump to our last classwork assignment here. Our last classwork assignment is 2x cubed minus 3x squared plus 4x plus 5. And this is all divided by x plus 2. So this one's not so bad. There's no x squareds that you're dividing by like in the last example. It's just, to test your ability here to make sure you understand how to do polynomial long division. So give this a shot. See what you can come up with. Okay, so the way you set this up, again, you put your divisor on the outside, x plus 2, and everything else on the inside, right? So 2x cubed minus 3x squared plus 4x plus 5. Now you say, okay, does this do we need any placeholders? No, we don't, right? We don't need any placeholders for our divisor. We don't need any placeholders for what we're dividing by, or I'm sorry, what we're dividing. So we don't need placeholders in general. We can just go ahead and continue with our normal operations. So we ask, what do we need to multiply x by to give us 2x cubed? And the answer is 2x squared, right? So now we take that 2x squared and multiply it by the entire divisor, x plus 2. So doing so, we have 2x cubed here, and then 2x squared times positive 2 gives me a 4x squared. And we subtract the whole thing. So now we have 2x cubed minus 2x cubed, which cancels out. And we have negative 3x squared minus 4x squared. So that should give us a negative 7x squared here. We bring down the next piece. I'm going to omit the arrow here, but we bring down the next piece. So we bring down that positive 4x. And the reason I know I'm only bringing down one piece is because I'm dividing by just two terms here, right? X plus 2. Okay, so now we ask, okay, x goes into negative 7x squared. How many times? What do I need to multiply by? Well, I need to multiply by a negative 7x, right? Negative 7x times x gives me a negative 7x squared, so perfect. And then negative 7x times the positive 2 should give me a minus 14x. So now we subtract the whole thing, which means the signs are going to flip for those pieces. So negative 7x squared plus a 7x squared is going to cancel out. So that's perfect. That's by design. And we have 4x plus 14x, which gives me 18x here. We bring down our last piece, which is that plus 5. So now we have 18x plus 5, and we ask, okay, what do I need to multiply by to give me an 18x, starting from our x here in our divisor, and right? 18 times x gives me 18x, so plus 18. And now 18 times x is 18x, just like we talked about, and 18 times the positive 2 gives us a 36. So we have plus 36, and we are subtracting here. So subtracting 18x minus 18x cancels out. 5 minus 36 gives me a negative 31, and that is my remainder, right? We can't divide negative 31 by x plus 2 any further, so we have a remainder here. So what is our final solution? Our final solution here is 2x squared plus 7x, wait, plus 7x? Minus 7x. I think it might be minus 7x, sorry. Minus 7x plus 18. And then our remainder, which we always put in whatever the sign is the sign that you put here. So negative, and now 31 over your original divisor, so x plus 2. And this is your final answer. Okay, so give the homework a shot. We're going to end this here. So basically, we've gone over dividing by factoring and dividing by long division. In the next class, what we're going to do is we're going to finish up long division. There's one last thing that I want to make sure that we talk about, and then we're going to talk about synthetic division and a couple theorems that fall out of synthetic division. Okay. All right, guys, enjoy the rest of your day, night, whenever you're watching this, and I will talk to you next time. Have a good one.